In this lesson, we will examine the wave mechanical model of the atom, which is also referred to the quantum model of the atom. This is the most current model of the atom and replaces the Bohr model of the atom, which was dropped because it was only useful for a one-electron system. As you know from the experiments we've discussed, Bohr was able to calculate electronic transition energies for the hydrogen atom. He was able to predict the amount of energy that was released when an electron in a hydrogen atom fell from one energy level to another energy level. When he tried to apply these calculations to atoms with more than one electron, these calculations failed. And as we investigate this model, we'll look at why his calculations failed. It was a German mathematician, Ernst Schrödinger, who devised the wave mechanical model through mathematics. He took into account the fact that electrons behave as waves, and he looked at the fact that rather than being able to identify the position and the velocity of an electron, one can only predict its position with a high probability. So rather than the electrons being placed in a position where we can identify them, as in the Bohr model with the electrons traveling around the nucleus like planets around the sun, he placed electrons in areas of space which he referred to as orbitals. We're not going to look at the mathematics behind this, but we're going to look at the qualitative result of the mathematics that Schrödinger did. And we're going to look at the areas of space, or the orbitals, as pictures, and understand that electrons can be found in these different areas of space. There are different types of orbitals of different shapes. There are S, P, D, and F. Our focus in this course is on the S, P, and D orbitals. You'll be able to reproduce the S and P orbitals, and you should be able to recognize the D orbitals. Now, the idea that Bohr had that electrons can only have certain types of energy continues to be an important part of the wave mechanical model. And the energy of an electron is shown in what is called the principal quantum number. So when an orbital is in the first energy level, it will be designated with a 1 in front of the label. So a 1s orbital is an s orbital that's in the first energy level. A 2s orbital is the same type of orbital, so it continues to be an s orbital, but it's part of the second energy level. Let's look at what these areas of space look like. As you can see from these diagrams, an s orbital is spherical in shape. The nucleus is at the center, and this is a three-dimensional area of space around the nucleus. So when there's an electron in the s orbital, what we say is that it can be somewhere in this space, but we cannot identify its exact position, and we cannot determine the path that it will take as it travels throughout the s orbital. What we can say is that there's a high probability that if we took a look, we would find that electron somewhere within that space. P orbitals have the shape of a dumbbell. The nucleus is at the center, and there are two lobes. If you want to draw them freehand, you could draw a figure 8. Now with an s orbital, because of its shape, there's only one orientation, only one way that we can look at the orbital. But there are actually 3 different p orbitals that orient themselves around the x, y, and z axis. So if we think about that, we've got our p orbital here, we've got a second p orbital, so we've got our y-axis and our x-axis, and then we can have a third p orbital that goes along the z-axis or comes straight out at you and goes into the page. For the d orbitals, there are 5 of them. And like I said before, you won't be expected to draw these, but you can recognize their shapes. So it's like two p orbitals in one plane, okay, at a 90-degree angle to one another. And there are 4 different planes with that type of d orbital. And then the 5th d orbital looks like a p orbital with sort of a donut area of shape. The key idea here is that if an electron were to be found in one of these d orbitals, it would be with a high probability that we would find it somewhere in the space defined by the orbital. Now, another important point to note is that each of these orbitals or areas of space can accommodate up to 2 electrons. So if we've got an s orbital, the maximum number of electrons that would be found in this particular area of space would be 2. No matter how simple or complex the orbitals are, they can each only hold up to 2 electrons. Now we discussed the principal quantum numbers, and so let's compare a 1s orbital to a 2s orbital. Okay, each of these are spherical in shape around the nucleus. Because the 2s orbital is in the second energy level, though, as designated by the principal quantum number, it will be larger, and it will therefore be found farther away from the nucleus. Okay, so the electron is in the center here, and the electron can be found anywhere in this space. Now let's take what we know from the Bohr model and use a new diagram to represent the location of the electrons within an atom. And this is how Bohr would have viewed an atom. So what we're going to do is take the information that we know from the Bohr model, and we're going to draw a different representation for that atom. And we're going to draw an energy diagram, okay, in place of the Bohr model with the nucleus and then the different rings getting farther and farther away from the nucleus. And much like with the Bohr model, where the rings are places that electrons can be held, we're going to, in this diagram, show orbitals where electrons can be held. Now, as you know in the Bohr model, 2 electrons can be held on the first energy level. And if we want to use an orbital to represent that instead, we know that we would require 1 orbital to hold those 2 electrons. In this energy diagram, okay, we're going to use horizontal lines to represent places where electrons can be held, or orbitals. So in Bohr's model, the first energy level would consist of 1 orbital. Now, as you know, in Bohr's model, we're able to hold 8 electrons on the second energy level. If we, in this diagram, want to show 8 electrons being held, we would require a total of 4 orbitals to hold those electrons. Okay, so all we're doing here right now is we're still representing Bohr's atom, but we're simply using a different style to represent that atom. So if you picture the nucleus here, and as we go farther and farther away from the nucleus, the electrons will have a greater amount of energy. So, and each of these, as you know, represents an orbital, or can hold, really it's a position holder for up to 2 electrons. So in Bohr's model, the third energy level would require 8 electrons if it's full. So again, another 4 orbitals are required. Now you may or may not have heard the phrase in earlier science courses where we say that the third energy level can hold 8 electrons, or 18. If we want to take into account the fact that it can also hold 18 and be full, we would need an additional 5 orbitals at this energy level. And we'll investigate that further as we move through this model. So what I want you to appreciate from this is that really this is just a different representation than the Bohr model, holding the same concepts. All the electrons in the second energy level are the same energy, and we've got a maximum of 8 on the second energy level. Moving farther away from the nucleus, we have electrons of higher energy, and at the third energy level we can hold 8 or 18. Now this is where we can start to see the flaw with Bohr's model. What Bohr was doing was he was doing calculations of electrons and the energy associated with them as they fell from one energy level to another. So he was able to predict in hydrogen the difference in the amount of energy between the specific energy levels within the atom. And this is where his system failed. He predicted that all the electrons in the second energy level had the same amount of energy, and all the electrons in the third energy level had the same amount of energy. The reality is, as you'll see from Schrodinger's model and a many-electron system, this is where the flaw was. Rather than all the electrons on the second energy level having the exact same amount of energy, there were what we now call sublevels. So within the second energy level, all these electrons are not at the same energy. Some of them have a certain amount of energy, and others have a different amount of energy. So let's look at how the diagram changes when we take that into account. Okay, so the first energy level still has just that one orbital. The second energy level has one orbital at a certain energy level, and then it's got 3 that are slightly higher in energy. So together, these still make up the second energy level. And all the electrons within these 2 sublevels have the same principal quantum level, or are part of the same major energy level. Okay, but as you can see, there are some electrons with slightly higher energy than the others. At the third energy level, there are 3 sublevels. Okay, so altogether, this set of orbitals makes up the third energy level. And this one down here is still the first. So let's make the connection between what we've learned about the different types of orbitals and label these orbitals more specifically. So here we're in the first energy level, so the principal quantum number of this orbital is going to be a 1. And if you look back at the diagrams, you know that when there's only a single type of orbital, our option is an s orbital. So the first energy level has a 1s orbital, and that is all. So if there are electrons found in the first energy level, they're going to be found in a spherical shape around the nucleus, somewhere within that orbital. This one here is also an s orbital, but it's now at the second energy level, so we'll label this a 2s. Now we've reached this set of 3 orbitals. We're still within the second energy level, so the principal quantum number is going to be 2. If you look back at your diagrams, the p orbitals consists of 3 orbitals, all oriented around the different axes. So we've got the px, the py, and the pz orbital. So in the second energy level, the reason some of the electrons are found at a different energy, slightly higher than others, is because of the type of orbitals that they're found in. So some of the electrons are found within a spherical orbital, but the electrons that are found within p orbitals are slightly higher in energy than those in the s orbital, which has led to these sublevels. In the third energy level, we have 3s, 3p, and then now we encounter this set of 5 orbitals, and these are the 3d. So in previous science courses, you focused on atoms with fewer electrons that were full after the 3p orbitals. And you really didn't deal with atoms that had electrons within this set of d orbitals. So that's why we didn't really address it in previous science courses. So this is the new basic diagram that we'll use to place electrons within atoms. And we'll discuss in a few minutes why we would use a diagram like this rather than a pictorial diagram where we drew the orbitals. Okay, so let's look at how we would describe an atom. Let's talk about hydrogen. Hydrogen has 1 electron. Okay, and with the Bohr model, you would draw the nucleus, and then you would draw 1 electron in the first ring around the nucleus. When we look at the energy diagram, when we've got 1 electron, the location of that electron would be within the 1s orbital. It's our very first lowest energy orbital. If we want to show an electron in this orbital, right now it's just blank, what we do is we use arrows to represent the electron. So this little arrow represents that we have 1 electron within a 1s orbital. So if you have an atom of hydrogen, what that means is that it consists of a nucleus with an electron somewhere within the 1s orbital. We don't know where it is. It doesn't need to be on the edge. It doesn't need to be in the center. There's just a high probability that we would find it somewhere within that space. Helium has 2 electrons. So helium's electron would be found also in the 1s orbital. There are 2 of them. As we've said, there's a maximum of 2 electrons per orbital. So for helium, both of its electrons are found within that 1s orbital, and the way that we show them is with the arrows. But when there are 2 electrons within the same orbital, they are said to be spinning in opposite directions. And we show that with the electrons drawn as arrows in opposite directions. If we look at lithium, it has 3 electrons. Okay, so much like we would fill the Bohr model and we would fill 1 energy level before moving on to the next, we will do the same with our orbitals. When we need another set of orbitals, we will add them in. So with lithium, it's got 3 electrons total. So its third electron will be found within the 2s orbital. Now we don't always want to draw a diagram like this, so we have what's called the electron configuration. The electron configuration is simply a list of the orbitals with the number of electrons that they contain. So for hydrogen, it's 1s1. For helium, it's 1s2. And for lithium, it's 1s2, 2s1. And the electrons are shown as superscripts. Now these are all called the ground state configurations of the atom because the electrons are in their ground state. They're in their lowest possible energy state. Now let's look at nitrogen. Nitrogen has a total of 7 electrons. Okay, so we'll place them. Got 2 electrons in the 1s orbital. Got 2 electrons in the 2s orbital. Now we still have 3 more electrons to place. And in this model, as soon as you need a sublevel, you draw all of them empty first. Okay, so we know we're going to need the 2p orbital, so we draw all of them. And then we're going to place those 3 electrons within the orbital. Now it's important to note that electrons will half-fill all of the orbitals within a sublevel before they start to pair up. So rather than placing 2 electrons in the 2p orbital and 1 electron in the second 2p orbital, they are spread out among the set of p orbitals. This makes sense if you think about the fact that electrons will repel each other, so they'd rather be spread out and have 1 electron in each orbital rather than having a pair of electrons in one area of space. Now another thing to note is that these 3 electrons, when they are placed in the orbitals in this way, they are all spinning in the same direction. You can have them all going downwards, right, but they just need to all be facing in the same direction. This will give the lowest possible energy state for this atom, which is what we are trying to achieve. So the ground state configuration for this is 1s2, 2s2, 2p3. Okay, so let's look at sodium. Sodium has 11 electrons. And what you'll notice is that we've got one major difference from the Bohr model to the wave mechanical model, that we don't have to show the nucleus and the protons and the electrons. Okay, the focus of this model is on the location of the electrons relative to the nucleus. Okay, so there are only 11 electrons. So you've got 2, 4, 10, plus 1. So an atom of sodium has 11 electrons, and this is the location of them. So what we need to be able to do is take this diagram and translate it into a picture. And this is where I hope you'll appreciate why we would use this energy diagram rather than trying to draw an orbital diagram. So what we have here is we've got the nucleus, right, and we've got the 1s orbital. So somewhere within that space around the nucleus, there are 2 electrons. And then we've got the 2s orbital. And somewhere in that space, there are 2 electrons. And then we've got our set of p orbitals, the px, py, and pz. And within each of those, there are 2 electrons. And finally, within the 3s orbital, there is 1 electron to be found. Now keep in mind, this is where the electrons would be found with a high probability. And I hope you can appreciate it would be really difficult if we used this style of diagram to represent these atoms, because it would be really difficult for us to show the orbitals and be able to identify where the electrons are. So this is why we use this more simple diagram, which we call an energy diagram. Now the electron configuration for sodium is 1s, 2, 2s, 2, 2p, 6, 3s, 1. Now, as you can appreciate, the more electrons there are within an atom, the longer the electronic configuration will be, and the less focus we'll have on the actual electrons that are involved in bonding and in defining the properties of a particular atom. So what we also have is what is called the noble gas or shorthand configuration of an atom. And this configuration focuses on the electrons in the valence orbitals or the final orbitals. And we do this by replacing the appropriate orbitals with what's called the noble gas core. And we find out what the noble gas core is by looking at the periodic table and identifying the noble gas that comes before the element that we're studying. So for sodium, the noble gas that comes before it is neon. And neon has a total of 10 electrons. Neon with 10 electrons, if we were to draw an energy diagram for it, would have this section here, be 1s2, 2s2, 2p6. So this section is said to be the noble gas core of sodium. So sodium really consists of neon core with a 3s1. So if we want to draw the noble gas configuration or write it out, what we do is we say neon and then 3s1. So each of these are appropriate representations for sodium. We've got our energy diagram, our electron configuration, and our noble gas configuration. And if you look at the periodic table that you have, or the one on the wall in the classroom, you'll see that all of the elements have a noble gas configuration listed. And it helps us to focus on the valence orbitals. So, as you know from before, sodium has one valence electron. And this is showing the location of that valence electron. Now, as we're filling the orbitals, we're actually following a process that's referred to as the Orbital process. And it simply means filling up principle. And some of these rules are old rules that carried over from the Bohr model and will make sense. And other ones are new that will help you to remember some of the rules about how to fill an orbital. So as you know, electrons are placed in the orbitals of increasing energy. So we start with the 1s and we move on from there. Each set of orbitals is completely full before proceeding to the next set. So we fill all the 2p before introducing the 3s, for example. Rules 3 and 4 together are referred to as Hund's rule, and they're related to the electrons that are filled within the same subset. So when we had nitrogen, and we had the 2p orbitals, and we half-filled them and had them spinning in the same direction, okay, we're following Hund's rule, which are rules 3 and 4 together of the Orbital process. So one electron is placed in each orbital before pairing occurs, and those electrons have all the same spin. Now, when we follow our rules for filling up an energy diagram, we're following what is called the Pauli exclusion principle, whereby all the electrons within an atom have what is called the same set of quantum numbers. And essentially what that means is that every electron within an atom is unique. It has a unique position and spin. And there are no two electrons within the same atom that are going to have the same orbital with the same spin. Now, as we move on past the examples that we've seen, the order of the orbitals is not as straightforward as one might predict. And there are some abnormalities in the order in which the orbitals are found within an energy diagram. We can use the periodic table to help us remember the order, and we can also use this mnemonic device to help us remember the order. The way that we set this mnemonic device up is we make a list of the orbitals by energy level and stacked. So in the first energy level, we only have the 1s. In the second energy level, we have 2s and 2p. In the third energy level, 3s, 3p, and 3d. And 4s and onwards has 4s, 4p, 4d, and 4f. Once we've got the orbitals written out and stacked in this way, then we can draw diagonal lines to know what the order of the orbitals are. So we draw a diagonal line this way. That shows us that 1s is the first orbital. Coming through this way, we see the next one is 2s, which is what we would expect. It's what we've seen before in our example. Followed by 2p and then 3s. Followed by 3p. And this is where we need to be careful. So one might expect, because the 3d is in the third energy level, that it would come next. But in actual fact, the 4s comes before the 3d. Okay, so 4s is actually lower in energy than the 5 3d orbital. So within the energy diagram, it will come first. When we examine the periodic table, we'll make further sense of that. Okay, after the 3d comes the 4p. Okay, and then we have 5s before we have the 4d. And the farthest we'll go in terms of drawing energy diagrams is 6s. Okay, but what you can see here is the s's come after the p's. Now another thing to note about how I've been drawing these diagrams is the way that I've been stacking all of the s's, all of the p's, and all the d's together. This is related to further concepts that are not covered in this course related to electronic transition. So we've talked about electrons falling from energy levels to other energy levels and releasing light. Now when electrons make these transitions, they will actually be more likely to jump within the same type of orbital. So a 2p electron will be upgraded to another p orbital and fall back down to another p orbital, rather than cross-jumping and going to an s orbital. So that's what this is trying to show or model in the diagram. Now if you look carefully at the noble gas configurations in the periodic table, you'll see that there are some unexpected electron configurations. What I've done here is I've filled in it in advance. But if you actually used the off-bow process to fill up the electrons in chromium, this would be the noble gas configuration that you would expect to see, with its valence orbitals being 4s2 and 3d4. For copper, you would find 4s2, 3d9 as the valence orbitals within that atom. Now, in actual fact, what happens is we have 4s1, 3d5, and 4s1, 3d10 instead. So what has happened here, if you just look at chromium, just look at those final orbitals for a moment, the expected configuration looks like this, where we have 4 d electrons. Now, what has happened is one of the electrons from the 4s has actually been upgraded in energy up to the 3d. So what we have ended up with is 4s, 1, and 3d, 5. Now, it has taken energy to bring this electron up to the higher energy level in the 3d. But the reason that it happens is because there's a special kind of stability that comes from the d orbitals all being half-filled. Them all being half-filled is actually lower in energy than having just 4 of them half-filled and 1 of them empty. So in the interest of stability, that electron will be raised up to the d orbital. And the same thing happens for copper and the elements within that same group. There's another certain kind of stability that comes from the d orbitals being completely full. So although it takes energy to bring one of these 4s electrons up to the d, the energy savings in having all of the d orbitals full has an overall benefit. Okay, so it's important to recognize that these elements do have unexpected electron configurations, and it's often that you'll be asked about these particular elements, okay, to make sure that you actually do know that they are unexpected. Now there's one property that we're going to discuss of atoms that can be identified based on the electron configuration, and that is the magnetic properties of atoms. Atoms can be referred to as either being paramagnetic or diamagnetic, and it's related to whether or not they'll be attracted to an external magnetic field. When an atom is paramagnetic, it will be attracted to a magnetic field, and when it is diamagnetic, it will not be attracted to an external magnet. And we can identify which one it is by seeing if there are any unpaired electrons. Okay, if we look at an example of a carbon atom, which has a total of 6 electrons, okay, compared to an atom of neon, which has 10. Okay, we can see that in carbon, okay, we are left with orbitals containing 1 electron that are not paired. If we think of the electrons as being magnets, if they themselves generate a magnetic field, when they're unpaired, they will be attracted to an external magnet. When you've got all the electrons within an atom paired up, their individual magnetic fields will cancel out because they're said to be spinning in opposite directions. So their ability to behave like magnets has canceled out with the other electron. So when you have an atom that has all paired electrons, it will not be attracted and is said to be diamagnetic. And when you have unpaired electrons, it is said to be paramagnetic. This is also evidence as to Hund's rule. If Hund's rule did not exist, and when we filled up in carbon, when we filled up the 2p orbitals, if we paired them together, we would expect that carbon would be diamagnetic because all of the electrons would be paired. Okay? But in fact, carbon is paramagnetic. It is attracted to an external magnetic field, and that is our evidence that the electrons, in fact, do distribute themselves the way that they do, spread out among the orbitals, singly paired, placed singly before they're paired. That concludes our formal lesson of the theory behind the wave mechanical model. It's really important to do the practice exercises, both in the textbook and the handout, because it will allow you to further investigate the periodic table and the connection between the electronic configurations and the setup of the periodic table. And in addition, you'll practice recognizing electron configurations of different elements and whether they're in the ground state or excited state, whether they're paramagnetic or magnetic, and identifying the noble gas configurations of elements. Okay, so there is a lot to be practiced in this lesson.